The best of money matters. Right Business.
Welcome to The Right Business, where we dive deep into the stories of trailblazers who dare to disrupt the status quo, find the gap in the market to find the right business. Hello, I'm Hongbin Jeong. Robots have become a fixture in industrial environments, from assembling cars to sorting packages, but they still face a major limitation. Most require extensive training on specific objects and can't handle anything unexpected. When a product changes or when objects appear in random orientations or unfamiliar shapes, traditional robotic systems struggle, slowing production and limiting flexibility. Now, this rigidness has become a major bottleneck for factories that want to be more adaptable, where a single assembly line could handle multiple product types or switch quickly between tasks. CynLr is tackling this challenge by giving robots the flexibility to adapt to changing products and environments, enabling factories to operate more efficiently and handle a wide variety of tasks with the same machines. They share more about how CynLr's technology brings human-like perception and adaptability to robots. Joining us today is Gokul, who is the founder of CynLr. Hi, Gokul. Welcome to the show.
Hi, it's a pleasure to be in the show.
Thank you so much for joining us. Well, Gokul, the story of CynLr seems rooted in solving problems that traditional robotic systems couldn't handle. So what exactly were those challenges in robotics and industrial automation that others weren't addressing, which led you to create CynLr?
I think the history of CynLr is also a bit old. We, along with my partner, has been at this for more than 15 years now, and we used to work with National Instruments previously. One of the major problems that we used to see with customers is, beyond price is always quoted as the major reason why robots have not been adopted in the industry, but beyond that, it's the problem of not having enough value for what they try to adopt in terms of robots. And robots do not essentially solve the issue of automation to the extent that the customer needs it to be profitable. So, and any investment into robotics even today, if you are supposed to adopt industrial robotic arm, 70% of the cost into the automation goes into customization. And customization for a customer is an unguaranteed or non-guaranteed outcome. Product is something that you know as per the spec sheets that it would work. But the rest of the customization that you're doing, which is 70% of the expense, is an experiment for the customer. And often that goes through a very long proof cycles, and essentially you have to do the project before you can actually win the order. So all these barriers and bottlenecks is not allowing customers to think their automation solutions through robotic arms, and simply because they are not repurposable and they cannot be modularly transformed without that 70% of cost that goes into environmental customization. And the scale of that, changes, even if it's a 0.2 mm of a dimensional change or the orientation change of the object, if not the shape of the object that you're dealing with, then all of this cost was waste, right? So there is no defensibility for the customer to invest into robotics today. That if there is a market change that happens, if the product design changes with your consumers and they have to, come back and then modify their car or their mobile phone or any of the gadgets or the components that goes into the gadgets to accommodate that design change, then this becomes the robot automation based cells become a barrier for them to do that. So these are major reasons, underlying reasons that is not often spoken about, but the major bottlenecks and barriers for the customer to kind of adopt robots today.
Okay, I mean, from creating the first prototypes to now building the CLX-1 Vision Stack and CyRo robots, how has CynLr's, mission evolved over time, Gokul, particularly as you've scaled your technology for industrial use?
When I talked about the limitations that customers face in adopting robotic arms, simply because the robots today need the orientation of the object fixed. If the object shape, dimension, or orientation or position changes, they cannot adapt and then pick them, right? So there seems to be a sensing gap in automation today. Putting a camera on top of a robotic arm is not just enough. You need a system that is capable of mimicking human adaptiveness in vision. That it should be able to observe from various angles. It should be able to see motion first, not just color. And it should be able to construct depth through various different information, not just stereo vision alone or just a pattern projection alone. So these are layers of technology that we identified that is missing. And we had to start building that from scratch. And evolution started from the vision platform first, which mimics the head of a human being, and then attaching all that meaning to what it sees as colors in terms of manipulation, touching, and the feel of the object and so on and so forth, which is what we manifested as CyRo, which is a 3-armed robot system, which is a little bit more flexible than what a human being can be, because all your head and both the hands can act independently and also be connected with each other and act in sync, but can be from 3 different viewpoints and so on, so which gives you a lot more flexibility to observe even in tougher situations that the human may have an access difficulty to. So, and it is all entirely real-time adaptive. So the last part that we evolved to is something that we call as the on-the-fly learning. That if a robot system is able to pick, learn, and handle an object live within 10 seconds, then any corner cases that you may not have foreseen while designing the robot is equipped to handle it by itself within that scene on the factory floor. So that's the layer that we came up with. And the last bit that we are adding now is the motion ability. The robot should be able to move around and then be able to access those objects, not just within the hand's reach. If there is something that is outside the hand's reach, then it should be able to kind of move and then pick them up. That is what we call a CyNoid as the last platform that we actually built. So we have a CLX, CyRo, and CyNoid.
Oh, that's very, very cool. Well, I mean, Gokul, you often talk about universal factories and the idea of one robot doing multiple tasks. Why do you think the current manufacturing setup struggles with flexibility until now?
This is linked back to the problem that I quoted, the underlying foundational problem that the industry has actually faced today. Design is today a slave of manufacturability, and manufacturability is a slave of the infrastructure that you have invested into. Now, to make a pen or let's say to make a spoon and a knife, you need an entirely different set of machines, right? But though they both are operating on the same material, and you have the same set of processes for you to get to that, right? Why? Because the shapes of the objects are different. That's because the shapes are different. Today, your machines are made as an outline to the shape. On the other hand, if only the same machine is able to adapt between multiple different varieties of objects, the infrastructure that is invested for spoons, if tomorrow demand is more higher for a knife or for a fork, then you can modify the same system just programmatically instead of having to rebuild an entirely new machine or new line, which is another machine, a factory, to build them. So this is similar to the vision that data computers have achieved. You would have seen that famous meme where in 1980s how many items were there in an office desk, and then that's all has been replaced into one laptop or one mobile phone. And if you want the laptop to behave like a fax machine or like a movie theater or like a calculator, it's just software away, right? You just change only in the software. You don't go and change and rewire your whole hardware or add pieces together. So today factories suffer this problem. They are all purpose-built as special purpose machines specific to one type of product and one type of component, right? That is what we intend to change, and that gets changed if that machine has the ability to adjust and adapt. Today, machines do not know what they're handling with. If you can give them the perception of what they're handling with, and they know how to adjust and adapt to the position variations, because every task is just simply a combination of picking, orienting, and placing. And all machines today are built to fix the position or orientation before picking, not after picking. A human being can pick in any natural state you present a part with and then orient later to mate it properly, right? So like if I give you a pen and cap, in whichever orientation you may give the pen and cap, you will be able to successfully bring them back and then mate them. That is not the capability the machines have today. And that's what we try to do, build what we call as an object intelligence and object sentience stack that will enable these robot systems to autonomously learn on the fly to bring them back and then mate them. So when this happens, the customer will be able to repurpose the same machinery and same infrastructure across wide varieties of products. That makes defensibility for the customer very high for investments that he actually puts in, and velocity of adapting to customer need changes or consumer need changes would be very high, and that's our goal, and that's what we envision as universal factories. Imagine all models of the car can come in the same, all platforms of a car can come in the same line. All models of your mobile phone can be produced in one single line. And based on demands, you can change from one mobile format to another mobile format. Right? So that's a huge reduction in the infrastructure cost and capital investment cost for a customer at the end of the day.
I mean, you've created CynLr, a platform that gives robots human-like perception and manipulation abilities, and you've described it as, enabling machines that don't just see but comprehend. So what does that really mean, and how does CynLr bring that vision to life in industrial settings?
I'll take a help of an analogy. If I tell a word, mango, or let's say an orange, right? So how does our brain go about interpreting that word? It's a random noise that fell in my ears. If I do not know the language, it's a random noise that fell in my ears. The brain tries to interpret that pattern of sound that fell in your ears by recollecting all the physical experiences that you had. So immediately my mouth starts watering when I say mango, or the shape and color of that object is visualized for me, and what my hand felt could be recollected. This is what gives meaning to that word. The experiences is what codes what the color patterns that you actually see from, without which a camera on top of a robotic arm is meaningless, right? And any amount of machine learning that you put on top of them is meaningless. We haven't understood sensing from perception. So you could add those sensors, but all the sensor data collating in a way where it formulates the idea of what an object is. That if I see a shape, it should mean in terms of it. I should be able to see what that means in terms of force, and in terms of touch feel, in terms of the weight that I'm actually picking. So this is what we call as the ability for the system to perceive. A baby need not have seen an object first, right, before. Yet it will go and pick it, put it in its mouth and throw it out, right? If I show a pen, it would have never seen a pen. It can stretch its hand, go pick it, grab it, put it in its mouth and throw it out. On the other hand, today a machine learning system, if it cannot label and then say that's a pen and a cap or A or B or whatever it is, it cannot go act on them. You need to know to act today. That's how machine learning is operating. But whereas human beings need not know an object to be able to act on them. So those are the object primitives that we call, that a baby is not looking at an object but a bunch of pickable contours, right? So, and then it can go and act on them. And the moment it sees those colors in the real world, it knows what the color means in terms of the force that I'm supposed to apply and how far it is and what is graspable, what is not graspable, and so on and so forth. That ability to discern is what we build into the robot systems, that if any scene it is being presented with, without having a prior information of those objects in the scene, it can successfully go touch them, pick them, interface with them. You'll also find that in our YouTube videos and things where we have shown some of those demonstrations. We keep them in the expos. People come and throw all the parts that they bring with. The system learns, tries to figure it out, pick it up, and then just instantaneously does it, possibly within 10 seconds or so. So that is the perception stack that we kind of entirely build.
Well, Gokul, you've also recently partnered with the Indian Institute of Science to push the boundaries of robotics by integrating insights from neuroscience. How does integrating neuroscience insights align with CynLr's current technology and vision? What unique advantages do you bring?
So one factor that we are acting on is the gaps that machine learning has today. Right, so that's the presumption from which, or the premise on which CynLr is being built. So when I have to, so the benchmark system that you're trying to automate is a human being, and we do not yet understand how the human brain actually works and what all are the dark regions that we haven't studied yet. Like as simple as, the computer vision today thinks that everything is about color. We have a color pattern of an object that we know, and we search for that in the environment to be able to locate that object. And if I'm able to locate that object, it will go and act on them. On the other hand, human eye does not see color first. It sees motion first, right? And it does not have just one way to construct depth. It has 18 different cues for it to construct depth, of which 6 will be very, very primal, and including motion, autofocus, convergence, and so on, so other aspects, because no scene in your real world is good enough for you to construct depth out of one method. You may have to employ different methods based on different situations that you're in. And then color is a very, very subjective information. That's why you had this blue and black and white and gold internet divide. Half of them are seeing the same dress as blue and black, and half of them are seeing as white and gold. That's how contrasting is color perception for a human being. And we can't take that as an absolute information. Now, all these layers, how this vision evolves for a human being is a largely not well understood layer in neuroscience and in machine learning also. And machine learning makes very fundamental assumptions of how neurons work. The kind of factors that we have achieved today, that it is able to do unlearned manipulation and on-the-fly learning, is just by imitating few layers of neurons. Imagine what would actually come about if we can understand all the rest of 7 layers and start implementing them. So what we do is we derive inspiration from how brain works and the neural layers that are there within, and then try to mimic them within our algorithms and try to understand how human beings are able to handle the same situation to such a generic case. So if we are looking at general purpose robotics, then we have to look at the general purpose human first, right? So that's the best machine that we have. And how its intelligence has evolved is what we want to study. And that's what we will start incorporating into the robot systems.
Looking ahead then, what else can we expect from CynLr in terms of technology partnerships or new applications?
So while humanoid interest is very high today, they are more manipulation focused. They are heavily sensing focused and sentience focused. And all layers that are needed for both the hand coordination and using the vision and hand manipulation and so on and so forth, these are the aspects that we will be working furthermore. So what we call as an object sentience layer is what we will be working into. Those are the primitives that the human beings have that even without knowing a scene, if anything that they can go and act on, right? So how that process evolves is what we will be building as stacks so that we can create a basic fundamental layer of learning intelligence or on-the-fly learning intelligence that can be adopted by not just CynLr's robots, but also other robots in the world. So we would be researching more into the vision. We will be researching more into the grasping. We'll be researching more into the dual hand manipulation also. A very simple task of putting a cap onto a pen is a very, very hard technology achievement today for robotic arms to achieve. So how does the process evolve in a human being and so is what is the tech that you'll actually build as a layer. Apart from that, you will also have few other products that may not mirror the humanoid, but will be more flexible than what a humanoid is and more industry ready for us to deploy into the manufacturing plants. So that will be the new set of products that will be releasing first quarter of 2026, apart from the current portfolio of products that we have now.
Amazing. Looking forward to it. Well, thank you so much, Gokul, for joining me today.
Absolutely. It was a pleasure talking to you.
Thank you. That was Gokul, founder of CynLr. This has been The Right Business with me, Hongbin Jeong.
To listen to more great interviews, download our podcasts at audio.sg or download the audio app. That's AWEDIO, audio at the App Store and Google Play.